Greetings, gentle readers. March 30, 2026. Reading foundations today is the topic. And it's meant to be read several ways. Kind of like when Heidegger is always balancing stuff back and forth. Reading foundations. The emphasis and the ordering, the accidence, as Kerm would put it in his Grammar of the English Language, has here that it's meant to just kind of refer to the idea that it's an experience, it's a learning experience to be familiar with common sense and practical wisdom first, and meeting life's needs, the Maslow's hierarchies sort of the material needs, without necessarily overdoing it. And then to get to the self-realization and self-actualization ideas, to make for that, there's a certain constancy or univocity for Duns Scotus, for the heicity of things, the thingness of things, the quiddity, and for the qualities of things. All these concepts from the canon of all the collected and received wisdom and literature, the knowledge, and with regards to wisdom and knowledge and intelligence and science, how those can be kind of a thing vis-a-vis broken apart in the deconstructive account. A canon, then a dogma, the ideas that arises, these are the truths. These are the truths and the principles of the things. The doctrine, meaning that deliberately and didactically and extendedly. And this is for a candidate for foundations. So this canon, the dogma, the doctrine, the candidate, foundations. So these are considered part of the requirements and desiderata of the theory, theoria, thea theory. If you've followed my readings or writings or these sorts of essays, you know a lot of these terms and phrases I use all the time, and that I reuse them all the time. They have a constancy in their meaning. For this constancy, about a consistency and completeness of the concreteness, then for the theory, as to why that's considered compelling, beautiful even, true for researchers and foundations of the sort. I'm not the most political person in the world. In fact, I rather care to stay a little bit more apolitical, and not just because it's associated with either the dirty tricks or the rhetoric of the iconoclast or bombastic sort. I consider myself a kind of a constitutional libertarian, which is not an anarcho-libertarian and is not an anarcho-capitalist and is not an anarcho-syndicalist, but a free market capitalist. And I believe in the common good, but not subsidies. And the cornerstones of equal rights and equal protections, then that for the rights, basically, that those are considered to be the fairest deal for everybody, the most egalitarian, where liberté, égalité, and fraternité are also great ideals received as since the influences of the United States' formation of government, Montesquieu and then Locke, and after Montaigne, and then for like Thomas Paine, a bit more of the radical sort, yet towards these ideals, and the Jeffersonian and so on. That these are arrived at as a fair deal, and so and so far as it goes, then I can not have to worry about things. When it's not like so, then I care, but I don't particularly feel involved. Why do bad jokes always come at the worst possible time? I don't know. Sometimes it's just because it's bad times. And then it's of these sorts of accounts where politics of when it's not statesmanship and brinksmanship, when it's not diplomacy, is considered poor, say. And so then that said, I really believe in the equal rights and equal protections, and then the idea of justice, the figure justice, with a blindfold, scales, and a sword, is when the scales get out of balance, the sword comes out. That's kind of the idea of this equal rights and equal protections and these kinds of things. So with that said, then, I won't comment much further on, for example, Aristotle's account of democracy as the rule of law. That's basically his definition, as after things like the Roman Constitution, after Polybius describes, giving a rule of law and for equal rights and equal protections, and these sorts of accounts. And then after the Hammurabic Code, and really the Golden Rule and all these sorts of accounts, those are considered proper and virtuous and all these sorts of things. And then with regards to Maslow's needs and hierarchies, that includes sometimes just kind of putting off those who are a bit too greedy, because it's a protection of the common good in a sense. Then the idea is that it can be so that in the great flow of material needs, as about the Malthusian dilemma. Malthus was a demographer. He arrived as like, well, the world's going to run out of stuff while people keep growing, thus catastrophe. And it's that's been put off so many times already that it's not a cyclic history, is the idea. And then with regards to that, in the course of human history, it's any different at all than like 100 years ago or 1,000 years ago or 5,000 years ago? It's a lot different. It's way, way different. And not just because of light bulbs and refrigerators and these sorts of things. The steam shovel, it's a lot different. So, good luck then. So today's this box of books about the quantum scale, the quantum theory, the mechanics of the quantum mechanics after classical mechanics. So classical mechanics is almost entirely concerned with rays and vectors, and notions of mostly after billiard balls. The billiard ball mechanics are kind of deemed as like, this is what gives us perfect inelastic collisions. Particles are as of after these are the pudding, the particle or the pudding model or this kind of thing. So as with regards to like Rutherford versus Dalton in the idea of the atomic physics, and then the old quantum mechanics, the old quantum physics, and then the Copenhagen quantum physics, and then in Copenhagen or Solvay, whether it's so that Copenhagen basically said, well, we got to treat everything as kind of indeterministic after Heisenberg, because it's so that it's going so fast that all we're getting out of is a sample. And then Solvay is a bit more about like, well, let's adopt Born rule too. So we're going to have Born rule and Pauli principle. Those are just kind of what's added. So that's not really new quantum mechanics. It's kind of like new quantum mechanics is Born rule and Pauli principle. That is basically there's no zero velocity. There's no rest in Born's land. Although Born's book, Max Born's book, The Restless Universe, tussles this back and forth quite a bit. Because when it gets to the idea of like the theory of images or whatever, how to establish the Lagrangian, because the Lagrangian makes the account of like, well, it's got to be balanced, the conservation of forces for the conservation of energy. And here it's all an inertial system. So momentum is not really the thing that's conserved at all. And in the quantum, it's also let out a little bit differently, and more about that later. But the approach of Lagrange makes for like, well, we got the potentialistic theory overall. This is that there's the energy, which is like, what's a particle? It's a quantity of energy in a particular form. Like Parseval in the macroscopic theory of matter, it's always of a particular form. And so then there's Lagrange with that idea, but then Lagrange also says, oh, by the way, as long as I'm doing that, I'm also going to give a way to put into the Hamiltonian to make for Hamilton and Jacobi, which is like these solutions for the Bra and Ket then is after that. So the great deal with quantum mechanics of Bra and Ket is like the conditional probability, because it's Bra and then the pipe or bar means conditional given that Ket, the other side of it. So it's taken the Hamiltonian's idea of the solution of systems of linear equations and differential equations, the eigenvalues systems, the eigensystems, and then putting in the middle of that, having basically then later after Solvay, then after Bohm and de Broglie, then it was made the Heisenberg picture and then Schrodinger. So Schrodinger picture enters into that. And so the Heisenberg picture is like, I don't know where it's going, but it's in a straight line from point A and back to point B, usually called P for the Heisenberg picture. And then Q for the Schrodinger picture, usually enough, is then it's like, well, it's a wave. And so that's the entire difference between the point and the particle, the billiard ball approach to mechanics, the classical. That's what's always called the classical, is just the Galilean. And then the wave, as after de Broglie. But of course, for hundreds and hundreds of years, it was argued back and forth whether light, for example, was a particle or a wave. I mean, it's not the new theory. It's just like putting back where it needs to go. The theory, the Schrodinger part of the picture. Then that's where it gets involved. These ideas of the collapse and where does it happen? Because it's kind of like if the Heisenberg account is only one way and nobody quite knows, then this Schrodinger picture is kind of like every which way and nobody quite knows. So how can it be that it is actually just a way and it actually has its value at any given time, the position and the energy, if not so much the momentum being derived from the energy, say, as a matter of velocity, but as for kinetics, because any of these particles are so equipped this way, whereas for the wave packet of the photon, massless and chargeless, that it has its energy still in these accounts. Then the idea is for how it can be a real wave collapse, a real wave function, because otherwise it's just kind of all these complex probability amplitudes that are given an account of that they form a probability distribution at all, because it's after Copenhagen given to be random, when really it could just be infinitely fast. And then this is the ideas of after Bohm and de Broglie, the pilot wave, or sometimes the ghost wave, that is just it's always going around faster than we can measure. So it's not like Heisenberg's uncertainty is like we can't know the position and momentum at once. It still has those. Heisenberg certainty, as it's called here. Then the Schrodinger wave collapse, and then the idea of the real wave collapse is also a way to get this back to being deterministic, causal sort of account of quantum mechanics, and that it has one, and that otherwise there's an account that there are either no laws in the universe or there's nothing ever actually fixed. So why there is the account of the probabilistic after the indeterminate is for measurement, sampling, and observation. It's like we don't have fine enough observations. Our instrumentalist or operationalist account of what is the position and momentum of this particle is formally let out as being underdefined. Is for energy also about getting into questions of, well, what about electron orbitals in the classic account? Why wouldn't they fall into degenerate orbitals and collapse into a point themselves, and these kinds of things? Why Heisenberg's uncertainty is a thing, besides the sampling, observation, and measurement effects, which is primarily, can be described as why it's a thing. And then the account then for the indeterminate is like, well, then it's got to be probabilistic because it does add up to what looks like waves, and these forms of these waves. Then gives an account for the Heisenberg uncertainty and Heisenberg certainty, and Schrodinger wave, and the Schrodinger real wave. And then that makes for after that like scattering and tunneling is supposed to, after scattering then tunneling is supposed to add up. Is like, well, how it disperses is wave-like in the radial and outward in all directions, while at the same time maintaining a classical path. And the path integral, as is read here or a couple years ago from a book on the path integral, the idea that somehow the quantum amplitudes add up to make a track or a course of particles motion. It travels through space in a gapless, jumpless, leapless manner since Leibniz, since definitions of continuity, since antiquity, for these kinds of accounts. Can make it so then, besides the idea that quantum mechanics has attached these supplementary variables after what were called hidden variables, the interacting terms, which were described even for things like Stern-Gerlach, the experiment, which is said to say, oh, we definitely proved that it's particles and discrete. Or not, it confirms itself to be agnostic then of the account of a real continuum mechanics for the supplementary and hidden variables of interacting terms. Then it gets into some of the mathematical formalisms to help describe then where do the numbers go to come and go from otherwise these places in these partial accounts, the partial differential operators, as what make the Laplacian, and besides in relativity theory is from last time's talk about double relativity and the Laplacian, and taking terms into those as an account of a reductionism, how to get back what's been made of this reductionism to have this anti-reductionism, more of a realism in the account, and to have it be mathematically formal and why that is so. So the idea here of how and why that is so is like to so. First, there's an account of the second partial derivative. And so with the second partial, or the partial derivative generally, you say, okay, it's a multivariate expression. Apply the rules of the differentiation with regards to one of these variables, treating the other values as constant. And then it results in that direction on that surface as it may be, it's like to so. That is its gradient of descent for things like gradient descent in generalized linear models and these kinds of things. Or the tangent. With regards to abscissa and ordinates in a coordinate system, the usual plain standard linear narratives account. So, and then that's holding everything else constant. But then when you take the second partial of that, now you can kind of look to see, it's like, well, that's second partial, but you took the second partial of the first partial. And so at least then all the other variables they introduce another term, at least one. So that's one way to look at it. And then how that gets expanded and brought in with regards to the Duhamel principle. And this is basically the idea that, well, this is one of the negligible terms, and the Duhamel principle is usually applied for sometimes finding solutions in systems of differential equations, because it happens to fit after an algebraic transform that you can get up out of it and back, finding a track, say. But then the other count is that there's always just an implicit term in the middle. So from the differ integral and integral differ talks here quite some time ago, it's arrived at the Duhamel makes, and along with, as I put it, Parseval and Plancherel, these kind of accounts as about this, and kind of in the same time as when Duhamel came up with this approach. He found some solutions in differential equations, but the principle applies that it's got this nominally non-zero term. So this middle term, say, or it's one of the interacting terms, or it's an implicit here, and these are all the correct sorts of names in mathematics for what it is. It has that then this interacting term is a placeholder for what's nominally zero, or nominally non-zero, here nominally non-zero, and then what's usually normally negligible. And so then all accounts of the analysis after taking the partial or any kind of numerical approximation gets lost. Eventually, it really often enough in the nonlinear, but otherwise in terms of feedback in the sigmoidal, in these sorts of accounts, is not lost. It's non-negligible. So that's where in the theories of what like the partial differentiation is where to apply to reemplace this what's an implicit an algebraic sort of quantity to have it like so, both for this double relativity theory and for this for these aspects of the quantum, the continuous quantum theory. And so then the idea here is, at least for 10 or 15 years, it's always been, and at least since 30 or 40 years ago, it's always been particle-wave duality. But for at least for 10 or 15 years, there's also been this wave-resonance dichotomy. And that makes for accounts of then for flow, which is like, this is the flow, it's at a steady, constant, finite rate. And the flux, which is abstractly all the way backwards from that, the backflow of it, say, flow and flux, for the energy in the entelechy, the great connected continuous surrounds, it's a continuous manifold, the background. It's a reticulated manifold, all infinitely detailed. It's a space and time together, space-time, and its contents, capital space-time, that these make for the wider account than otherwise the particle in the classical wise, which, just as described, gets broken apart and lost in the wash, as it's called, of the momentum operators, which is not conserved. Momentum is not conserved. That energy is conserved, and that forces are conserved. Potentials are conserved. Potential forces in overall the fields, and the fields as they are of the potential fields, the real fields. So it's a field theory, and then a gauge theory to explain this kind of nonlinearity. It's unlinear, these sorts of things. So this fits with otherwise the standard sort of account with or without Solvay, with or without Copenhagen, kind of with both of Heisenberg and Schrodinger and like non-Heisenberg and non-Schrodinger together, to give why the mathematics will give mathematics that conform in the conformal with the behavior as it's observed of quantum mechanics. So continuous quantum mechanics. Do they already have one of those? In bits and pieces. Yet by the time people learn all the formalisms and get above where it's just like, well, here's the Schrodinger size function, you'd have to solve it to solve the wave equation, make it real. And these sorts of accounts, like, well, how do they do it? It's like, oh, they get a partial half account, call it good enough. It's engineering in this sense. How about particle wave duality? It's like, well, that's a good question. I mean, we're still trying to figure out whether something can rest or move at all. And that gets there's lots of accounts about that in the moment and motion bit, because that's really a question for mechanics itself, and mechanics and its concepts in the Lagrangian and Maupertuis and least action and this kind of stuff. That here it's always not just a sum of histories and a least action. It's a sum of histories, sum of potentials, least action, least gradient. That equilibrium is always at equilibrium, sequent equilibrium. And that's a natural sort of account of things. So in this box of books has quite a number of texts about quantum mechanics. Now I'll just be trying to just go through these at a clip, at a pace, and seeing what's in them. So briefly, hopefully for your amusement, there'll be something in here that if you find this of interest, then you could follow on for yourself and find out more about it. This book is about 120 years old. Its price is A Treatise on Infinitesimal Calculus. So right before the turn of the 20th century, pretty much. See, this was from 1900, the Free Public Library of the city of Trenton, New Jersey. The Seal of Trenton, 1792. And this is a kind of a classic book. A treatise on infinitesimal calculus, containing differential and integral calculus, calculus of variations, applications to algebra and geometry and analytical mechanics, by Bartholomew Price, M.A.F.R.S. F.R.A.S., fellow and tutor at Pembroke College and Sedleyan Professor of Natural Philosophy, Oxford. Volume 1, Differential Calculus, second edition. He quotes Dupin as saying, "Le progrès de la science ne sont vraiment fructueux." The progress of science will not truly be fruitful, que quand ils amènent aussi le progrès de traits élémentaires, until it amends itself better to the progress of elementary treatises. Oxford at the University Press. And so today it's always called real analysis. It's not called infinitesimal analysis, because here to have standard infinitesimals is pretty much like to have the line rails, as after things like the fluxions and influence of Newton, or Leibniz's raw differential, obviously in concept always a way, that it was real analysis was always called infinitesimal analysis before. It was just called real analysis. The character of infinitesimal calculus. Everyone who has watched the progress of the science will hardly need to be told of Sir W.R. Hamilton, Cayley, Boole, Donkin, Spottiswoode, Sylvester, Salmon, Hargrave, or any more than of Jacobi, Dirichlet, Joachim Stahl, Hesse, Plucher, Steiner, Sturm, and Liouville. To all these in their several degrees is due the credit of having brought the subject to a state of perfection never heretofore attained, and a treatise pretending to be didactic and educational would ill deserve those epithets if the discoveries of such eminent mathematicians were not noticed in it. So I'd mentioned here it's about Duhamel and Parseval and Plancherel being added, basically. It's kind of a concept of his lectures. And he thanks Navier, Gregory, and Professor de Morgan, the author of the treatise published by the Society for the Diffusion of Useful Knowledge. And then Donkin and Spottiswoode are both of his Oxfordians. And generally, too, to the journals of Liouville and Crelle. Mines of precious materials to the mathematical student. Liouville's encyclopedia of information was for Liouville, and then Crelle's journal is well known for a long time as the premier venue for advances in mathematics. Infinitesimals, very small. In the light of differences between two states at a very small distance apart, they have obtained the name of differentials instead of differences, and hence the name of differential calculus has arisen. The notation also in language of Lagrange's calculus of derived functions has been employed. So that gets in a lot about the functional analysis and this sort, referring again to Lagrange, because it expresses in a most convenient form some of the earliest results of operations with infinitesimals and the relations to finite quantities. But I would warn the reader especially against supposing that our calculus is founded on the notion of derived functions as the coefficients of the term of the series. They are not considered in that relation at their first admission, relating that approximations have nominally non-zero error terms, and also with regards to the analyticity, and hear about the implicits and these sorts of other reasons why the author is indicating they're not to be admitted at first admission, but they have their own caveats. He goes on. Expansion in a series has been admitted fundamentally but once. Dirichlet in Article 21, and whatever may be the final issue of the question as to convergent and divergent series, it cannot affect that which I have employed, inasmuch as it is proved to be convergent. He's talking about the access, the exactness or the perfection of the differential and integral calculus. It's perfect, meaning it determines areal terms or higher dimension terms from lower dimensions terms, according to the use after the geometric series, and an usual account of the methods of exhaustion, as it was called since antiquity, and the approximations for the area of the circle, and how it was worked out that there's a value for pi, and via calculus, via the methods of exhaustion and analysis, then this is just giving an account as like, this is how it is perfect, and that there's these sorts of accounts that need to be so to make it so. Otherwise, it's merely partial or just an approximation. Talks about thus a finite number of infinitesimals is neglected if it's added to or subtracted from a finite quantity. Here, there's an account for the line reals, the iota values as real numbered or real valued that basically don't have both of sums and products. And so it's not they don't admit, as it were, that they have otherwise these characters of arithmetic that would break them or result in being inconsistent multiplicities, is the usual account after a descriptive set theory is given that there would be. So infinitesimals to have real analytical character that's really all what matters to make them so that have them be mathematical quantities and not just descriptive or qualities of things. So there's a difference between infinitesimal as a quality and infinitesimal as a quantity. And here the only infinitesimals that are quantities are these iota values, the standard infinitesimals. Between 0 and 1, it's not just divided infinitely many times, it's infinitely divided. And then the resulting constant, monotone, strictly increasing elements range from 0 to 1, and they have extent, density, and completeness of measure. It's a continuous domain. That would be the basis that would fit perfectly well with this account of the infinitesimal analysis, because it doesn't say more than that would otherwise make it so that the author here would have had to qualify this differently. So Maclaurin's account of infinitesimal analysis has a very good reading into this, and Maclaurin's account of the infinitesimal analysis is about the best one of the time. And then this account of Price is a great. I was very gratified to find a work in a textbook from this time, and in a single source sort of work. That then this book from the Oxford University Press of I suppose this is in Roman numerals. I'd have to read out 1918. 57? I'm not sure how to read what year this would be in. As where though it's as from Trenton Library and this part of thing. So then it gets to know many sorts of accounts as would be parts of an analysis and real analysis. Expansions. Differentiation of functions and many variables. Section 2, from functions and many variables. On functions and many variables. When many variables are involved in an equation, it's theoretically possible so to arrange them that one shall be a function of all the others, whereby it becomes an explicit function of many variables. And these latter variables may be independent of each other or have such relation amongst them that a variation of one may involve a variation of one or more of the others, whereby the number of independent variables may be diminished. The former case, which is more general, shall be first considered, and then such modifications. So the usual count, this is not directly just partial differentiation. It's usually written as, of course, instead of like, it's just a little Latin d for the differential. That's like the marker for a differential. And then d squared is like the second differential. Then the curly scripty Greek little d or delta is for the partial differential. That's always written that way. And this is after Leibniz's notation for the differential. Or Leibniz. Infinitesimal variation. Total variation or total differential, and the former, this latter is called a total variation or a total differential, and the former are called partial variations or partial differentials. Thus we have variations of the growth of 4 distinct kinds. A variation due to each of the 3 causes acting separately in the whole variation, which is the sum of these 3. So this is something I looked to study a little bit more, is after something like Tullio Levi-Civita is the absolute differential calculus, and here with regards to total variation and total differential, and then with regards to partial variations, a partial differential. because for the Parseval and Plancherel to make it for the accounts and for examples of make it for accounts of this Duhamel principle and adding them back together and reconstruct the place for what partial differentiation or the Laplacian and for the Poisson and the usual account of after grad and del of the operator according to all the things like Navier and Stokes after Green's function and all this, the partial account is where it would go. It would then be related to these sorts of things as to what it would intend to repair. Then it gets into differentiation of an implicit function of two independent variables and so on. Without the expression being put in the form of an explicit function of one variable. So reading Price's Infinitesimal Calculus, Treatise on Infinitesimal Calculus, as this edition happens, and I think this is from about the year 1900 is where it is. Not quite sure how I'm to read this copyright date in the Roman numerals, does directly address some of the issues that go into why quantum mechanics or continuous quantum mechanics has this as part of its course. It's a continuum mechanics is usual idea. Infinite crossed products. Donald S. Passman. And I got this book. It's algebraic, Grothendieck groups and induced modules, graded rings, and then it's about taking like a functional account of like, well, what happens if you have like the direct sum or the direct product or to find otherwise a product of these crossings of the products, then what these are to be about these things. Prime ideals, the Noetherian case, so not any Noether, but the next Noether, that fellow's account. So the algebraic, G prime coefficients, the finite case, X-inner automorphisms, the Martindale ring of quotients, polynomial identities, Maschke's theorem, Akiyama's lemma, these accounts getting into algebraic modules, the stable ideals, vis-a-vis the skews, and then figuring out that he'll define at some point what are the crosses after permutations, given he's defined star as a product, and for polynomial identities in this development, it's quite thorough, there's a lot going on, and then some proofs by contradiction, mentioning from the finite to the infinite case. Furthermore, we have made a diagonal change of basis. So this is getting into the crossing of things. It's like, well, it's linear. It's like, well, what happens? It's like, well, it turned. So how does it maintain the analyticity about these things in a sense? Prime ideals. So usually most people think of primes as about the numbers and prime factorizations. And then there's an account of something like, well, what about the p-adic integers after Simon Steven? It's like, well, they're kind of like infinitely long integers, because you know when you multiply two numbers, two integers, positive integers, they'll be on the order of the sum of their orders. It'll be on the order of like 10 times 10 is like log 10 base 10 is 1, and log 10 base 10 is 1, and then multiplying them together is log base 10 of 100 is 2. So you sum those orders, the orders would add up. So that's like the big end of the p-adic integer, p-adic, p-adic. And vis-a-vis something like the l-adic integers or something like that. So on the little end of it, though, it's like addition. It just increments one after another. So when you increment on the side on the little end of that is like an integer, and otherwise about primes and figuring out what's going on with their factors, and then also with regards to the integral moduli when increments to change reach them, are about these prime ideals and the prime-adic integers and these sorts of things. Free rings and subrings, group actions in Galois theory, So groups are reductionism usually. Grothendieck groups. This results asserts that the Grothendieck group of a Noetherian cross product R star G, the product, is determined in a well-defined manner by the subcross products R star H for the various finite subgroups H a subgroup of G. This is very pretty in its own right. It also has far-reaching, surprising applications. So that's saying what the Grothendieck group is it's kind of like tensors then, is that the Grothendieck group is a number of different things according to whether it does this, according to this. So that would be kind of a way to take that sort of development and then getting into all the entire Langlon's program as showing its independence about various concerns. Oh, here's Fritz London. Great. By Fritz London, Superfluids, Macroscopic Theory of Superconductivity, Volume 1. So this book is called Superfluids, Macroscopic Theory of Superconductivity. So superconductivity is where in the accounts of, kind of like in the quantum mechanics, it's like, well, how fast would the direction have to be going around a particle as a wave, so when it's a wave that it collapses, it appears random, infinitely fast, super. It's like divided by zero. That is what it is. It's infinity. And so then the superfluids are accounts of things like, well, what happens when resistance goes to zero? And then for something like Ohm's law and Kirchhoff's law, it's like that would mean, otherwise that would be in the terms what it means that its reciprocal goes to infinity. So there's a picture of Fritz London, 1900-1954. And so this is a second revised edition with a new epilogue, theoretical developments 1950-1960 by N.J. Buckingham, School of Physics, in the University of Sydney. So I'd be wondering if this is related or the same as for the account of dimensional analysis, the Buckingham pi account is for natural units and these kinds of things. That here instead there's considered a more dimensioned account. And for the dimensional alternator, dimensional resonator, which are accounts of like, well, it's meters per meters. What does that mean? Well, algebraically it means zilch. It just means one. It doesn't mean anything. But what it means is when it has a tendency or propensity back and forth, like the x squared plus minus 1 bit and these kinds of things from the moment in motion account, which kind of addresses and touches on some of these things, and also from the descriptive differential dynamics. That's kind of where like the x squared plus minus 1 came up a lot, and also with regards to the dimensional analysis, that being more in the moment in motion bit. Here though, this is about Fritz London, and this is a reprint from Dover Reprints, Dover Publications Inc. Copyright 1950 by Edith London, 1961 by Dover Publications. There's acknowledgments from Edith London, who is Mrs. Fritz London. So I'm going to leave this aside and look at this because I was this has some great expressions that would help to be so like just some kind of like Price's account of the infinitesimal calculus, the total differential, the total variation. Then there's some expressions for that in London as well that will be relevant. They are the mathematics of continuity and infinity. This book is called The Grand Contraption. The World is Myth, Number, and Chance by David Park. Princeton. It's a history, it says. Physics, astronomy, geology, and poetry all come together here in the grand quest to understand what our universe is and how it works. From a professor of astronomy and the history of science at Harvard-Smithsonian Center for Astrophysics. See, what I was reading here is measuring months and years, Earth and Heaven. So this is a cosmological account. And he's talking about wisdom and these kinds of things. The Tao. Ma'at, RTA, logos, wisdom, and number refer to principles of justice and proportion and beauty. With them, there is little or no sense of enforcement. But Te and Ananke are stronger. They prescribe and enforce. Because we're talking matters that cannot be seen or directly experienced, we float among metaphors, but always in one form or another, the idea of law recurs. Allowing for differences in expression, it seems the world is made so that behind what may seem to be random acts of nature, caprices of gods and men, there are guiding principles that should or must be obeyed. For many people, though not for someone who thinks only atomistically, this law has something to do not only with necessity, but also with justice and moderation, or even with beauty and fitness, as in musical harmony. It is strange that a law that governs equity in human affairs can at the same time tell the planets where to go. Remember that in ancient times, all matter was perceived as being in some sense alive. Cicero quotes Aristotle as writing in a work that has otherwise vanished. What remains then is that the movement of the stars is voluntary. Here that would be just random, say. Because what we take from Aristotle is circular movement is eternal, but there is no unmoved mover. But here, though, quoting Aristotle by Cicero is saying, what remains then is that the movement of the stars is voluntary. That basically gives a third sort of account to go along with these accounts of Aristotle that I'd consider now adding that with among these Aristotle's accounts. Kind of go with the accounts of like the three laws of large numbers and these other sorts of ideas. There is no unmoved mover. Circular movement is eternal. So it wasn't ever moved, yet it moves, yet it moves. And this account that the stars, the movement of the stars is voluntary. These being the most remote and distant items, individuals. And that would fit with a usual account is for principles of why that's for just matters of motion and so on, the random motion, as with regards to rest and so on as well. For example, voluntary. That voluntary implies that there's an own kind of animism towards it. And then the author says, rereading the last few pages, I'm reminding of a line I copied from the Rig Veda long ago. Truth is one, the wise call it by different names. That this is kind of reflected upon as the conflation, confusion, and other matters of items together and their deconstructive accounts and these sorts of things. And this other section where I'd been reading was about Galileo, the world observed, Galileo and Kepler, Newton, system of the world, reactions, transformations, conversions, the texts, matters of medicine and biology, a theory of matter, Newton, who never in his life left England. Science was leaving Aristotle behind, but the vision of ancient wisdom remained like the glow in the evening sky. For stellar distance, William Herschel's map of the galaxy, the age of the Earth. Darwin and birds. Darwin had read Malthus. Alfred Russel Wallace. The 1920s. Einstein's closed-in universe, wrapped in mathematics that few could fathom, provided an attractive solution to the problem of infinity. But in 1930, the British astronomer Arthur Eddington showed that such a universe would be as unstable as a pencil balanced on its point. The slightest change in the densities of matter and energy would set it either expanding or contracting. And of course, the stars radiate energy. Those densities are always changing. This encouraged astronomers to look at a paper called The Expanding Universe that Eddington discovered in 1931 at an obscure Belgian journal, caused to be published in the monthly notices of the Royal Astronomical Society. Its author was Lemaitre. About just accounts of extrapolation in the asymptotic, or the infinite. And this is according to that both the Big Bang hypothesis and the steady state hypothesis fit the data in some way, and neither are falsifiable either way. So That's a universe, though. Closed systems can have their own sorts of accounts. Well, let's see here. Some little while left in this thing. The covering property axiom, CPA, a combinatorial core of the iterated perfect set model, by Christoff Szyselski and Janusz Palikowski, Cambridge University Press, Cambridge Tracts in Mathematics 164. So when we talk about the Rulio accounts of the regularities in set theory, there's well-foundedness and well-ordering and well-dispersion, also called Martin's axiom, also called univalency, also called illative, for after like Berendrate, after homotopy type theory, but after Martin's axiom, and then for his accounts since atomism, it's kind of just an account that things spread out, the dispersion. So a covering property axiom would also be like, it's like just like illative and univalency makes like, it's not just a pairwise union, it's an infinite union of things. Then I'd only imagine if this was going to be an axiom added to a set theory, a combinatorial core of the iterated perfect set model, that this would be as of such an account. And where I was reading in it, some consequences of cofinality of n equals omega 1. So the cofinality of a set is kind of like, you know how we can only count upwards, and the set is infinite, so we'll never get there. Well, what's the rest of it? Cofinality, and so then when that's in some cases it gets to arguments is like, well, that can't be countable and it can't be uncountable, and so here's an account of that it's uncountable. The omega 1, the omega is the ordinal. The ordinal omega has a cardinal aleph 0, so that's omega 0, and then the ordinal aleph 1 is the first uncountable ordinal. It doesn't say whether that's aleph 1. It just says that it's the first uncountable ordinal, because according to various models of ordinals and various accounts of the continuum hypothesis, various theories with or without choice of the well-ordering principle, it's going to vary because it does. It's independent, those accounts. So the authors here are considering something like that about this thing. About ultrafilters. So ultrafilters, and here, this is great. Ramsey, recall that a non-principal filter f on omega said to be Ramsey, provided that for every b and f and h b squared on the 0, 1, there exist I less than 2 and a and f such that a less than b and h of a squared in this bracket equals I, this set. It's well known that an ultrafilter on omega is Ramsey if and only if it is selective. So that would be for Dirichlet, because the accounts of the ultrafilter are almost always given to Dirichlet, and the for the pigeonhole principle and this kind of thing, it's like it's dense. So it's usually enough statement of density, or it can be shown to be so for some particularly usual things. Talking about Rozlanowski and Schiller. Below we note that each of these properties contradicts CPA cube. So they set up one where it's like you would need another axiom to make this other property hold that would be like so, which is fair. Here there's an account, or after the Rulialities and regularities, that there's each of well-ordering and foundedness and well-dispersion, and then they have to go together somehow in a non-contradictory way, because otherwise the authors still will end up showing a way that their theory otherwise that has this as an axiom, they can make it constructively so that it would make a contradiction. Implies that there exists a CPA game cube, implies that there exists an uncountable lambda set in R that is strongly meager. So it's that this is that it was like, well, there'd be like a huge subset of R. And the various formalisms that derive at this. So now that I kind of better know the language of this, I'm going to read this a little bit more a little bit later. So where then is projective determinacy? It's also kind of like Martin's axiom. The powers that be, global energy for the 21st century and beyond. So this is kind of apropos. Scott L. Montgomery's The Powers That Be, Global Energy for the 21st Century and Beyond. About global energy, a beautifully written, highly engaging book that tackles nothing less than the general global problem of energy. Here there's an account basically to use Fischer-Tropsch after the electrolysis of carbon dioxide and carbon monoxide and the electrolysis of water to hydrogen and oxygen to make liquid fuels and kind of solve the liquid fuel problem, that being a carbon neutral process. And then it takes a ton of electricity, which here is for an account of renewables largely, but then in big fusion seems to be a good idea, because big fusion is, or maybe even just little fusion, could possibly make it so that makes a lot of electricity. The idea that I've seen it coming up is the one where they just they have a toroidal moment and they just pulse it, and then it makes an electromagnetic pulse, and then that just kind of gets flushed off and makes an electrical current, electrical potential, and thusly a pressure gradient, this kinds of things. Many years of experience in the energy industry. Talks about oil, coal, nuclear power, the renewable energy, hydrogen. Hydrogen is a great thing because if you have any kind of energy at all, then you can use electrical current to split water into hydrogen and oxygen. And then gathering the hydrogen isn't so difficult out of that. And then it just kind of has to be used kind of quickly, and it's very volatile, and it leaks out of anything. And if you put it in a metal tank, it embrittles the tank and it won't keep. And then people have approaches for like, we'll put hydrogen in matrices or lattices, or the nickel hydrides and these sorts of things, which are kind of like, as according to a chemical reaction, they very rarely can be attached and detached with that much energy or volatility. But hydrogen is a great way to store energy. It's very volatile though, and this kind of thing. Fusion energy, geopolitics and energy, climate change and energy. Conclusion. Final thoughts on new beginnings. Many notes. So trying to understand like the situation of energy in many case studies about it could be read from this book. Strategic issues. Rich nations vis-a-vis other nations that are just as rich in their own way. There's no single energy crisis. Instead, the world faces a number of partly interrelated energy challenges. The Malthusian. And like there's a Malthusian dilemma, and then kind of like the Malthusian delight, it's like, wow, we really can make it work without the Malthusian dilemma and these sorts of things. Nuclear power. Public ignorance has considerable power in a democracy like the U.S. And as well, like giving people information and knowledge, it has even more power. The middle class is the most important thing to keep well, because you can't have a rich and prosperous nation unless you have a prosperous middle class, because otherwise you won't have a rich and prosperous nation. You'll just have the plutarchy, as it's called. And so that's not the same thing because the nation is comprised of individuals. So the middle class is really the key thing that needs to be supported. And that goes around for everybody in terms of standards of living and what's deemed an acceptable standard of living. It's like the Maslow's pyramid and all this kind of stuff. And then also independence. So you have both productivity and opportunity at the individual and small and group collective level. Well, it's about an hour or so. We have gotten not very deep yet in this box of books, but I was very happy to find that book on of London's, and I'll be looking at that. This is Hermann Weyl's Levels of Infinity, Selected Writings on Mathematics and Philosophy, edited with an introduction by Peter Pesic, P-E-S-I-C, or Pesic, I'm not sure. Edited with an introduction. Weyl's, Dover reprint, Levels of Infinity. Polynomials, talk about Hilbert and his work, Levels of Infinity. Mathematics and Logic, Brouwer's Intuitionistic Mathematics. There's Millebrand of Axiomatics. Zmirlo very strongly brought after well-foundedness, also well-ordering. Talk about Christoffel and Levi-Civita, and I'd be careful to refer to Schoenflies when talking about Christoffel and Schoenflies, and the combinatorial or crystallographic classes. Antisymmetric rule. So while relativity theory is a stimulus in mathematical research, so it's like, well, now that we've given this is what relativity theory must do, how is it done? Well then, general readers, that's today's reading foundations. Bit of continuous quantum theory. Warm regards.